These are the notes for standard 2.5, which is solving problems with two objects that are moving, at least one of them with a constant acceleration. And to describe this standard, we're just going to do two example problems. So the first problem has a dog running at a constant velocity and steals a bucket of Halloween candy from a child mid-stride. If the child can accelerate at a certain acceleration, where will they catch up to their candy? And so to draw a diagram, I've got the beginning of the situation when the dog takes the candy, and we can write those values that we've got from the problem around these things. Notice that the diagram helps us to sort out those given values and make sure that they're positioned near the object that they apply to, which will help us later when we are plugging them into multiple equations. Then I've drawn what happens at the end of this situation. This is when the child catches up to the dog to reclaim their candy. And this is important just to see that they start in the same position when the dog steals the candy, and then they end in the same position when the child gets the candy back. And so ultimately, they have the exact same displacement for this problem that we're trying to solve. So the givens are the velocities of each, the person and the dog. Remember that at rest is a velocity, and for the child, that velocity is 0 meters per second. Notice in the givens here that I have added some subscripts. In addition to the I for initial velocity, I've also put a D for dog and a C for child in order for me to just make sure that I can keep them sorted as to which values correspond to which object or which moving body. Our unknown is where will they catch up to the candy, and so that is that displacement, how far they'll be from where the dog steals the candy from the child. For equations, we've got lots to choose from, and here we have to be very careful as we are choosing them because for the dog, we have to choose a constant velocity equation, seeing as the dog isn't accelerating at all. It just tells us that the dog is moving at a constant velocity. And so ultimately, we can use the bottom one, and we can subtract the initial position from both sides to make it a more simplistic equation that solves for the displacement of the dog. Then for the child, we can't look at any of those equations because the child is accelerating. We also don't really need to look at the acceleration due to gravity because nothing is falling in this problem. And so then looking at the other equations that we have not eliminated so far, we're looking for one that has an initial velocity, an acceleration, and a displacement. And so we're going to use the top one and again make a similar adjustment so that it is solving for the displacement of the child. Because we don't know anything about the final velocity of the child, that's how we could eliminate some of those other constant acceleration equations. For our substitution, we've gone and plugged in the acceleration of the child and the initial velocity of the child, as well as the initial velocity of the dog. And you'll notice that this is a little different than in our past problems, because in our past problems, we would substitute for all of the variables except for one, which would allow us to then solve for that variable. Here, we have two equations, and therefore we can be comfortable with having multiple variables still in the equations. So we've got the displacement of the child and time in the left equation, and the displacement of the dog and time in the right equation. But because we have two equations, it is okay to have two unknowns. To solve them, what we're going to do is I basically simplified this substituted equation. And so I've got a coefficient of 0.05 times time squared, and then because the initial velocity of the child was 0, that term cancels out. For the dog, it's simply 2 times the time. And now that we have these two equations, we can remember what I said with the diagram, which is that the displacement of the child and the displacement of the dog when they catch up to each other is the same. And so what we can do is we can set these two equations equal to one another, which then allows us to just solve for the last variable that we don't know, which is time. So we can divide both sides by t, and then divide both sides by 0.5 and get that it will take 40 seconds for the child to catch up to the dog. But remember that the problem is not asking how long will it take for the child to catch up. The problem is asking where and what is the position that the child will have when they catch up. So there, what we have to do is we have to take that time and then plug it back into either of our substituted equations in order to find what the displacement was. And so I've shown here, this is what it would look like if we plugged it in for the child's equation. This is what we would do for the dog's equation. I would recommend that if you have the choice between a constant acceleration and a constant velocity equation in order to plug a time back into, use the constant velocity one because it is usually simpler as it doesn't have any terms that are squared. So the answer to this problem is that in 80 meters, the child would catch up to the dog and get their candy back. In our second problem here, we have two race cars, and they're near the end of a race. One car is leading and is 100 meters from the finish line, traveling at a constant velocity of 50 meters per second. The trailing car, the one that's not leading, is 120 meters from the finish line and traveling at 55 meters per second. And the question is, what acceleration would that car need in order to tie the leading car? So here's my diagram. We've got two cars approaching the finish line, and I can put the velocities that were given. The car that's farther away has a velocity of 55 meters per second. The one that's closer has a velocity of 50 meters per second. But then labeling this diagram with initial positions really becomes important, and we have to make these decisions deliberately. So we know from the problem that the front car is 100 meters away from the finish line, and that the trailing car is 120 meters from the finish line. An easier way to label this would be that it's 20 meters behind the leading car because that total distance now is 120 to the finish line. Now, what we need to do in order to start solving equations is label these cars and the finish line as specific positions. And the easiest way to do that is to picture them on a number line. So there's a couple different ways we could do this. We could say that the finish line has a position of 0, and then we could say the leading car is 100 meters left of that finish line, or negative 100 meters, and the trailing car is a negative 120 meters from the finish line. And this is one way that you could describe the situation, which the number 100 and 120 directly come out of the problem and are applied to this number line. But if negative symbols make you a little bit uncomfortable, like they do me, another way that you could think about this is you could say that the car that's in last place right now, or in second place, it has a position of 0 meters, and then we could just number from this position relative how far this leading car is from there. And so because it's 20 meters away, we could say it starts with a position of positive 20 meters. And because the finish line is 120 meters away from this back car, we could say that it has a position of 120 meters. And so this is actually the perspective that I'm going to be taking for the rest of this problem. But again, those negative values would get us the same result. For givens, we have lots of information. Remember that this 100 and 120 meters actually shows themselves in the initial positions of the leading car and the trailing car. I've done the same thing as the last slide, which is I've added another subscript, L and T, in order to differentiate between which car I'm describing with these different physics values. The unknown that this question is asking for is the acceleration, specifically of the trailing car. So when we're looking at equations, we have to be careful like we were in the last problem, because these two cars are moving with different types of motion. And so for the leading car, we need to look at a constant velocity equation. And I'm going to choose the bottom one because it has a final position and an initial position, which we now have for the leading car. For the trailing car, because it is accelerating, we're going to use an acceleration equation. It's not falling, so we're not going to consider the acceleration due to gravity. And so the top one is the best choice for that car. as well. To substitute into these equations, we're taking the given values. Notice that for the final position of both cars, we're going to put the same final position because we want them to end up at the finish line at the same time. And then we can solve. Now, in these two equations here, for the leading car, we have just one unknown, which is time. So we can fully solve that equation and calculate that the leading car is going to get to the finish line in 2 seconds. But then in the other substituted equation, we have for the trailing car, we have an unknown acceleration and an unknown time. So once we solve for the time that it would take for the leading car to get there, we can plug that in and then solve this equation for the acceleration, which would make the trailing car get to the same location at the same time. And so the result is an acceleration of 5 meters per second squared, and that is a mistake. There should be a squared on that seconds. For solution methods, I showed you algebraically how to solve these two problems, but you could also solve them graphically. So for the first problem with the dog and the child, this is a graph of their motion. The dog is described by the red line, and the child is described by the blue line. And so if we are careful in developing those position time equations, we can solve them in and then, we can enter them in and then see when the times and the positions are the same. And so in this case, it's at 40 seconds and 80 meters where they cross. For these problems, a couple of themes that you will recognize and should use to your advantage is that usually these equations are related by time, because time is in both constant velocity and constant acceleration equations. And for something to cross or to meet at a specific position, it'll take the same amount of time for two things to get there. So if you end up with an equation that has two unknowns, but one of them is time, you can feel comfortable, as we did in both of these examples, because you'll be able to either solve for time or eliminate time and then solve for it later. Thank you.